There are places in the ocean where the environment begins to behave in ways that feel familiar at first, and then slowly stop making sense. Tonight, we are moving toward one of those places. The place we are heading sits at the bottom of the ocean, in depths so remote, so cold, so completely cut off from the world above, that when scientists finally found ways to look down there, they expected to find very little. What they found instead has been quietly rewriting the science books ever since. There is a lake at the bottom of the ocean, not a metaphor, not a trick of light, a real body of water sitting inside the ocean with its own shoreline, its own surface, its own gentle waves. You could theoretically swim up to the edge and look across it. The water inside is so dense, so different from the ocean surrounding it, that the two simply do not mix. They sit beside each other like oil and glass. And that is just one of them. The deep ocean is full of places like this, places that look familiar from a distance and stop making sense the closer you get. Coral reefs blooming in permanent darkness, hundreds of meters below where any light has ever reached. Sounds recorded in the abyss that puzzled researchers for years, low, vast, and unlike anything produced by weather or geology or any known creature. Landscapes that mirror the surface world, mountains, valleys, plains, but governed by entirely different forces, home to entirely different kinds of life. For most of history, we assumed the deep ocean was simple, barren, a cold, dark, featureless place where nothing interesting happened. Every time we send something down to look, that assumption falls apart a little more. And here is the part that makes researchers genuinely uneasy. We have seen so little of it. The technology to explore the deepest parts of the ocean is still in its early stages. What we have found so far, the lakes, the coral, the sounds, the creatures that should not exist, represents only a fraction of what is down there. There are places on the ocean floor that no instrument has ever reached, places where the rules we rely on may not apply at all. We do not yet know what we are missing, and in science that is the most interesting place to be. So tonight, we move slowly into the strangest, least understood corners of the deep ocean, the places that surprised the scientists who found them, the places that are still being figured out, the places that remind us, gently and repeatedly, that this planet is far stranger than we give it credit for. If this kind of slow journey into the unknown is what brings you here, a like and a subscription keep these explorations going, and they mean more than you might think. Let's descend. Before anything unusual appears, the ocean arranges itself into quiet, unseen boundaries. These divisions are not marked by lines or edges, but by gradual shifts that change how light moves, how pressure settles, how life chooses to exist. From above, the surface seems continuous, a single open expanse. Beneath it, the water separates into layers that behave almost like different worlds resting on top of one another. The uppermost region carries the memory of the sun. Light enters here in full strength, scattering across drifting particles, illuminating currents, touching everything with warmth and motion. This is the zone where familiar life gathers, where color still holds its meaning, where sight remains a reliable sense. Energy flows easily, driven by sunlight, shaping ecosystems that resemble those on land in their complexity and abundance. Yet even here, the brightness is already thinning, softening as it travels downward, absorbed piece by the water itself. A gradual dimming leads into the next layer, where light no longer dominates but lingers. In this middle depth, illumination becomes uncertain, filtered into faint blue tones that stretch and fade. Shapes lose their sharpness, and color begins to disappear. Red vanishes first, then orange, then yellow, leaving behind a muted world where everything blends into shadow. Organisms adapt by shifting their reliance away from vision, developing other ways to navigate, to sense movement, to find one another in the dimness. The transition is subtle, yet it marks the beginning of a deeper separation from the surface above. Below this, the ocean releases light entirely. Darkness settles in fully, not as an absence that feels temporary, but as a permanent condition. No sunlight reaches here, no matter how clear the water above may be. The environment becomes defined by what is no longer present. Vision changes meaning, often replaced by sensitivity to vibration, to chemical traces, to faint pulses of energy. In this vast midnight region, life persists in forms that rely on internal sources of light, brief glows that flicker and vanish, signals exchanged in silence. The absence of sunlight does not end activity, but it reshapes it into something slower, quieter, more deliberate. As depth increases, another force becomes impossible to ignore. Pressure builds steadily, compressing everything with a consistency that never relents. Each descent adds weight, layer upon layer, until the force pressing inward becomes immense. Materials behave differently under such conditions. Structures must adapt or fail, and life forms that exist here are shaped by this constant compression. Their bodies hold together through subtle biochemical adjustments, proteins stabilized in ways that allow them to function where most would collapse. At the lowest reaches, the ocean settles into its deepest layer, a region that remains largely untouched. The abyss stretches across vast distances, a landscape hidden beneath kilometers of water, where temperature hovers near freezing and pressure reaches extremes that challenge even the strongest machines. Exploration becomes difficult here, not because of distance alone, but because every descent demands precision, strength, and time. Instruments must endure crushing forces, navigation becomes uncertain, and communication with the surface grows fragile. These layers do not exist in isolation, yet they shape everything that happens within them. Movement between them is possible, but never simple. Energy diminishes with depth, conditions grow more restrictive, and the familiar rules from the surface begin to loosen their hold. This structure explains why so much of the ocean remains unseen. Most exploration pauses within the upper boundaries, where technology and human limitation meet, and it is within the deeper layers, beyond the reach of light and routine observation, that the most unusual environments begin to appear. There are places on the seafloor where the water seems to hesitate, as if it has reached a boundary it cannot cross. The descent into these regions reveals something that does not behave like the surrounding ocean. A flat reflective surface appears below, holding its shape with quiet precision, separated from the water above by a thin, wavering line. It resembles a shoreline, seen from an unfamiliar angle, not carved from land, but formed entirely within the ocean itself. These formations were first observed in parts of the Gulf of Mexico and the Red Sea, where dense brine has gathered into contained pools. The water inside them carries an extraordinary concentration of dissolved salts, far beyond what the surrounding ocean holds. This difference in density creates a barrier that is both delicate and stable. The heavier liquid settles into depressions along the seafloor, while the less dense seawater rests above it, the two layers resisting the urge to mix. Along the edges, the boundary becomes visible. It shimmers faintly, disturbed by subtle currents that move across it without fully breaking it apart. Small ripples travel along the surface of the pool, responding to motion above as if it were open air rather than water pressing from every direction. The effect is disorienting, a quiet illusion of separation in a place where separation should not exist. Movement across this boundary brings consequences. Creatures that drift too close often cross into the brine without sensing the change immediately. Within moments, their bodies encounter a chemistry they are not prepared to endure. Oxygen becomes scarce, replaced by compounds that interfere with basic biological processes. The transition is abrupt, and survival is rare for those not adapted to these conditions. Along the margins, still forms sometimes remain, marking where the boundary has claimed them. Yet within the pools themselves, life persists in a different form. Microbial communities gather along the interface where the contrasting environments meet. These organisms do not rely on the patterns of energy found above. Instead, they draw from chemical reactions, using compounds dissolved in the brine to sustain their existence. Their processes unfold slowly, almost imperceptibly, forming thin layers that shift in color and texture depending on the balance of elements present. The chemistry within these pools reflects conditions that were once more common on a younger Earth. In environments where oxygen was limited and chemical gradients shaped survival, similar processes may have guided the earliest forms of life. The resemblance is not exact, yet the parallels remain strong enough to draw attention. These isolated pockets offer a quiet reference point, a glimpse into a time when life adapted to constraints that now seem distant from the surface world. The stability of these pools is not absolute. Currents above them continue to move, temperature shifts occur, and geological changes alter the shape of the seafloor over long periods. Despite this, the boundaries endure, maintained by the persistent difference in density and composition. The balance is delicate, but it holds, allowing the pools to remain intact for years, sometimes longer, though their full lifespans are not yet fully understood. Seen from above, they rest like still lakes in a place where stillness is unexpected. Their surfaces reflect faint traces of light carried down from higher layers, creating a muted glow that outlines their form. Around them, the seafloor continues, as it always has, shaped by currents and time, while within them, a separate environment unfolds, governed by its own quiet rules. A faint column rises from the seafloor, dark against the surrounding water, unfolding upward in slow, continuous motion. It does not drift like ordinary sediment. It pours, as though something beneath the crust is releasing its contents into the ocean above. The plume thickens, curls, and expands, carrying with it a heat that does not belong to the cold depths around it. These structures were first encountered in 1977, when instruments descending along a mid-ocean ridge recorded unexpected activity. What appeared at first as irregular signals soon resolved into towering formations, mineral chimneys built over time by the steady flow of fluid from below. They stand in clusters, some narrow and fragile, others rising like pillars, each one venting a stream of water heated far beyond the temperature of the surrounding sea. The fluid emerging from these vents begins its journey deep within the Earth's crust. Seawater seeps downward through cracks in the ocean floor, drawn into regions where magma lies close beneath. There, it is heated and enriched with dissolved minerals, transformed into a dense solution that rises back toward the surface. When it meets the cold ocean, the minerals precipitate rapidly, forming dark clouds that resemble smoke, though they are composed of fine particles suspended in the water. Around these plumes, an unexpected community gathers. The seafloor here is not empty or quiet. It is structured, inhabited, shaped by the continuous release of energy from within the planet itself. Creatures cluster along the chimneys and surrounding rock, forming dense assemblages that contrast sharply with the more sparse regions nearby. Among them are long, pale organisms anchored to the substrate, their bodies extending upward in gentle arcs. These tube worms lack mouths and digestive systems, yet they persist in large numbers. Within their tissues, symbiotic bacteria carry out chemical processes that convert compounds from the vent fluid into usable energy. The worms provide a stable environment, while the bacteria sustain them, a partnership that replaces the need for traditional feeding. This exchange reflects a broader pattern within these vent communities. Life here does not depend on sunlight, which never reaches these depths. Instead, it draws from chemical gradients, from the interaction between reduced compounds rising from below and oxidized seawater surrounding them. This process, known as chemosynthesis, supports a network of organisms that have adapted to a source of energy entirely separate from the one that shapes most ecosystems at the surface. The realization that such systems could exist altered long-held assumptions about the limits of life. It suggested that biological processes might arise and persist in environments previously considered uninhabitable, guided not by light, but by the steady flow of chemical energy. The implications extend beyond the ocean, offering a framework for understanding how life might develop in other places where sunlight is absent. Yet, even within this understanding, questions remain. These vent fields are not permanent. Individual chimneys can become inactive, their flow diminishing as geological conditions shift. New vents emerge elsewhere along the ridge, creating a pattern of transient habitats scattered across vast distances. How organisms move between these isolated sites, how they maintain continuity across such a fragmented landscape, remains only partially understood. The structures themselves continue to grow and collapse, shaped by the same processes that sustain them. Mineral deposits build layer by layer, while the internal flow of fluid carves pathways that change over time. The entire system exists in a state of gradual transformation, neither fixed nor fleeting, but constantly adjusting to forces that originate deep beneath the seafloor. Within these rising columns and the life that gathers around them, the ocean reveals another way of sustaining complexity, one that unfolds quietly in darkness, guided by energy that never passes through the sky. Far below the reach of daylight, structures begin to rise that resemble forests in their form, though no leaf has ever unfolded there. Branching shapes extend outward and upward, delicate and intricate, building themselves over spans of time that stretch far beyond human observation. They do not sway with wind or respond to sunlight. They grow in stillness, guided by processes that unfold in silence. These are deep-sea coral reefs, formed by organisms that construct rigid skeletons, layer by layer, generation after generation. Unlike their shallow water counterparts, they exist without the influence of photosynthesis. No light reaches them, no energy arrives from above in the form of sunlight. Instead, they depend on nutrients carried by slow-moving currents, tiny particles drifting downward from distant regions, settling into the structures and sustaining the life embedded within them. Growth here is measured in increments, so small they are almost invisible. A few millimeters over the course of a year can shape an entire branch. Over centuries, these increments accumulate, forming vast frameworks that stretch across the seafloor. Some of these reefs have persisted for thousands of years, their oldest sections holding a record of conditions long past, preserved in layers that continue to build upon themselves. The architecture they create is complex, filled with openings, overhangs, and sheltered spaces. Within these structures, life gathers in quiet density. Small organisms find refuge in the narrow gaps. Larger creatures move slowly along the outer surfaces, and countless interactions unfold within spaces too small to observe directly. The reef becomes more than a structure. It becomes a habitat, a place where existence is shaped by proximity and shelter rather than light. Color behaves differently here. Without sunlight to reveal it, Pigments lose their usual purpose. Some corals appear pale, others take on subtle hues that only become visible under artificial illumination. These colors are not signals in the same way they are near the surface. They are remnants of biological processes, expressions that no longer serve the same role, yet persist as part of the organism's form. The water that moves through these reefs carries more than nutrients. It brings a constant exchange, removing waste, delivering new material, shaping the environment in ways that remain steady over long periods. The currents are gentle but persistent, tracing paths through the structures, influencing where growth occurs and where it slows. Over time, the reef adjusts to these patterns, expanding in some directions while remaining sparse in others. Despite their resilience over centuries, these formations are fragile in ways that are not immediately visible. The same slow growth that allows them to persist also limits their ability to recover. When disturbed, sections can break or collapse, and the time required to rebuild extends far beyond a human lifetime. In some regions, damage has occurred before the reefs were fully documented, leaving only fragments to suggest what once existed. The difficulty of reaching these depths has meant that much of this environment remains only partially understood. Exploration continues to reveal new structures, new communities, each one adding detail to a landscape that has been forming quietly for millennia. The reefs do not announce themselves. They remain where they have always been, expanding slowly, holding within them a record of time that unfolds at a pace almost imperceptible. In the absence of light, these forests continue to grow, shaped by currents, sustained by drifting particles, existing in a balance that has endured long before they were first seen. There are places where the seafloor does not level out, but instead folds downward into long, narrow depressions that descend far beyond the surrounding landscape. These trenches trace the boundaries of shifting tectonic plates, where one section of Earth's crust slips beneath another, drawing the ocean floor into depths that remain among the least accessible on the planet. They extend in quiet arcs across the Pacific and beyond, their full scale difficult to grasp even when mapped. Among them, the Mariana Trench and the Tonga Trench reach the greatest known depths, descending more than 11 kilometers below the surface. At these extremes, the distance between surface and seafloor becomes almost abstract, a vertical span that compresses time and motion into something slow and deliberate. Light, long absent, has no role here, and the environment settles into a uniform darkness, shaped instead by pressure and cold. The weight of the ocean above accumulates steadily as depth increases until it reaches levels that challenge the integrity of nearly every material. Each square centimeter endures a force that would collapse unprotected structures, compressing spaces, altering how substances behave, reshaping the boundaries of what can persist. Instruments designed to explore these regions must be built with careful precision, their forms reinforced to withstand conditions that allow little margin for error. Yet, within these trenches, life continues. Among the most notable inhabitants are snailfish, small and translucent, their bodies adapted to an environment that would overwhelm most organisms. Their tissues are soft, lacking rigid structures that would be vulnerable under such intense compression. Instead, their internal chemistry provides stability. Certain molecules accumulate within their cells, balancing the pressure from outside and preserving the function of proteins that would otherwise lose their shape. Proteins, which carry out essential processes within all living cells, are particularly sensitive to pressure. At great depths, their structures can distort, interfering with the reactions they enable. In trench organisms, subtle modifications allow these molecules to remain functional. Compounds such as trimethylamine and oxide appear in higher concentrations, acting to stabilize protein folding, ensuring that biological processes continue even under extreme conditions. These adjustments occur at a microscopic level, yet they define the boundary between survival and collapse. The trenches themselves are not uniform environments. Their walls slope at varying angles. Their floors collect fine sediments that settle slowly from above, and occasional disturbances reshape their contours. Organic material, carried downward over long periods, accumulates in these depths, providing a limited source of energy for the organisms that reside there. Movement is minimal, interactions are sparse, and life unfolds at a pace that reflects the constraints of the environment. Despite advances in exploration, much of these ecosystems remains uncertain. Observations are limited by the difficulty of reaching such depths and maintaining equipment in place long enough to gather continuous data. Each expedition offers only a brief glimpse, revealing fragments of a system that extends far beyond what can be directly observed. The relationships between species, the full range of biodiversity, and the processes that sustain these communities over time are still being assembled from scattered observations. Within these trenches, the ocean reaches its deepest expression, a place where familiar expectations give way to conditions that reshape both matter and life. The descent into these regions reveals not emptiness, but a quiet persistence, carried forward in forms that adjust to pressures few environments can match. Across vast stretches of open water, instruments once recorded a boundary that should not have been there. Echoes returned from a consistent depth, forming a line that resembled the seafloor, steady and continuous, as if the bottom of the ocean had lifted itself upward. Yet this boundary did not remain fixed. It shifted slowly, rising and falling over the course of each day, tracing a pattern that repeated with quiet precision. This phenomenon became known as the deep scattering layer, a dense aggregation of small organisms suspended within the water column. From a distance, it behaves like a surface, reflecting sound waves in a way that mimics solid ground. Early sonar systems, interpreting these signals, marked it as the ocean floor itself, unaware that the boundary was composed not of rock or sediment, but of countless living forms moving together. As observation improved, the movement of this layer revealed itself as part of a daily cycle. During daylight hours, the aggregation remains at greater depths, compressed into a relatively narrow band. As darkness approaches, it begins to ascend, spreading upward through the water in a slow, coordinated migration. By night, it reaches shallower regions, dispersing more widely before gradually returning downward as light returns above. The organisms that form this layer are small, often no larger than a few centimeters, including fish, crustaceans, and gelatinous creatures. Individually, they are almost insignificant in scale, yet together they create a structure vast enough to influence how the ocean is measured. Their bodies contain materials that reflect sound efficiently, creating the illusion of solidity where none exists. This vertical movement is driven by the balance between feeding and exposure. In the upper layers, food is more abundant, carried by currents, and concentrated in regions influenced by surface processes. Moving upward allows these organisms to access this resource, but it also brings them closer to potential predators. Remaining deeper during the day reduces visibility, offering a degree of protection that shapes the rhythm of their migration. The scale of this movement extends across oceans worldwide, forming one of the largest coordinated migrations on the planet when measured by total biomass. Every evening, An immense quantity of living matter rises through the water, and every morning it descends again. This pattern unfolds continuously, largely unseen, repeating with a consistency that reflects both environmental cues and biological necessity. Despite its extent, much of this process remains only partially understood. The exact composition of the layer varies by region, influenced by temperature, nutrient availability, and local ecosystems. Measuring it accurately presents challenges, as its boundaries are not fixed and its density changes over time. Advances in acoustic technology and direct sampling have improved understanding, yet the full complexity of this movement continues to emerge gradually. The presence of this shifting layer alters more than perception. It influences how energy and nutrients move through the ocean, linking different depths through its daily migration. Material consumed near the surface is transported downward, contributing to processes that unfold far below. In this way, the movement of small organisms becomes part of a larger system, connecting regions that might otherwise remain separate. What once appeared as a misplaced seafloor now reveals itself as a living boundary, rising and falling with a rhythm that has persisted long before it was first recorded. Sound travels through the ocean in ways that differ from what is familiar above, carrying across distances with remarkable efficiency. In the absence of light, it becomes one of the primary ways the environment reveals itself, moving through water as vibrations that persist long after their source has faded. Beneath the surface, this creates a layered soundscape, one that is continuous, shifting, and only partially observed. In the late 20th century, a series of recordings captured a signal that stood apart from the usual patterns. It was low in frequency, broad in its range, and powerful enough to be detected across thousands of kilometers. The signal rose in intensity, then tapered off, its structure unlike known biological calls or geological events at the time. It came to be referred to as the bloop, a name that reflected its unusual acoustic profile. For a period, the origin of this sound remained uncertain. Its scale suggested a source of considerable size, yet its characteristics did not align clearly with known marine life. Over time, further analysis and comparison led to a more grounded explanation. The sound was consistent with the fracturing of large ice masses, a process in which stress within the ice builds until it releases suddenly, producing a distinct acoustic signature. As ice shifts and breaks in polar regions, these signals can travel vast distances through the ocean's interior, arriving far from their point of origin. This resolution did not diminish the broader realization that the ocean is filled with sounds that remain only partially cataloged. Alongside identifiable sources, there exist numerous clicks, pulses, and low-frequency tones that have yet to be fully matched to specific processes or species. Some are brief and localized, others extend across wider areas, their patterns repeating with a consistency that suggests biological activity, though confirmation remains incomplete. The ocean structure supports the movement of these sounds in complex ways. Variations in temperature and pressure create layers that bend and guide acoustic waves, allowing them to travel along paths that extend far beyond what might be expected. In certain regions, sound can become trapped within a channel, moving horizontally for great distances with minimal loss of energy. This property turns the ocean into a medium where signals can persist, overlap, and interact. Within this environment, many organisms rely on sound as a means of communication and navigation. Calls pass between individuals, reflections provide information about surroundings, and subtle variations in frequency carry meaning that remains difficult to interpret without direct observation. At the same time, geological processes contribute their own signals, from the shifting of the seafloor to the movement of fluids beneath it. The result is a continuous acoustic field, shaped by both life and the physical structure of the planet. Despite this richness, only a small portion of the ocean's soundscape is actively monitored. Recording equipment is limited in its coverage, often placed in specific locations for defined periods. Vast regions remain unobserved, their acoustic activity passing without being captured or analyzed. What is known comes from fragments, assembled over time, offering glimpses into a system that extends far beyond the current reach of measurement. As more data is gathered, patterns begin to emerge, linking certain sounds to known sources while leaving others open to further study. The process is gradual, guided by careful comparison and verification, avoiding conclusions that extend beyond available evidence. In this way, the ocean's hidden acoustics continue to unfold, not as isolated anomalies, but as part of a broader system that is still being understood in quiet increments. Beneath layers of sediment, where the seafloor appears still and undisturbed, a different kind of structure forms in the spaces between grains. It does not resemble rock in the usual sense, nor does it behave like ordinary ice. Within these buried regions, methane becomes locked into crystalline cages of water, creating a substance that holds gas and solid together in a quiet, stable arrangement. These formations are known as methane hydrates. They develop under conditions of low temperature and high pressure, where water molecules organize themselves into lattice frameworks that trap methane inside. The result is a material that looks like compacted frost, yet contains a concentrated store of energy within its structure. If brought to the surface, where pressure decreases and temperature rises, the lattice breaks apart, releasing methane gas and leaving behind water. Across continental margins and deeper sedimentary basins, these hydrates accumulate over long periods. Organic material drifting downward is gradually buried, where microbial processes break it down, producing methane that migrates through the surrounding layers. Under the right conditions, this gas becomes incorporated into hydrate structures, building deposits that extend across large areas of the sea floor. In some regions, these accumulations form continuous layers, while in others, they appear as scattered pockets, shaped by local variations in temperature, pressure, and sediment composition. The scale of carbon stored in this form is significant. Estimates suggest that methane hydrates may contain more carbon than all known fossil fuel reserves combined, though the exact quantity remains uncertain due to the difficulty of measuring deposits beneath the seafloor. This reservoir exists largely out of view, its presence inferred through indirect methods such as seismic imaging and drilling samples that reveal the characteristic structure of hydrates. Despite their apparent stability, these formations are sensitive to changes in their environment. A shift in temperature, even by a small margin, can alter the balance that maintains the hydrate lattice. Warming of bottom waters, changes in pressure due to sediment, movement, or geological disturbances can cause hydrates to dissociate, releasing methane into surrounding sediments and, in some cases, into the water column above. This release can occur gradually or in more concentrated events depending on the conditions. Methane itself is a potent greenhouse gas, capable of influencing atmospheric processes if it reaches the surface in sufficient quantities. Much of the methane released from hydrates is consumed by microbes or dissolved in the ocean before it can escape, yet the potential for larger-scale release remains an area of active study. The interaction between hydrates and climate is complex, involving feedbacks that unfold over long timescales, making precise predictions difficult. Evidence from geological records suggests that past changes in climate may have been linked, in part, to the destabilization of methane hydrates. Layers of sediment preserve chemical signatures that indicate periods of increased methane release, though the exact mechanisms and triggers continue to be examined. These records offer a glimpse into processes that operate slowly, often beyond direct observation, yet capable of influencing broader systems. At present, the stability of methane hydrates is maintained by the same conditions that allowed them to form. The cold temperatures and high pressures of the deep ocean create an environment where these structures can persist over extended periods. However, as ocean conditions evolve, the boundaries that define this stability may shift, altering the distribution and behavior of these hidden reservoirs. Within the sediments, the hydrates remain largely unseen, embedded within a landscape that appears unchanged from above, holding within them a form of energy that rests quietly beneath the ocean floor. When a whale's life ends far from shore, its body begins a descent that unfolds slowly through the water column, settling at last upon the seafloor. The fall is not sudden in its consequences. It marks the beginning of a long, quiet transformation, one that reshapes a small portion of the deep ocean into something briefly abundant, then gradually returns it to stillness. The arrival of such a body introduces a concentrated source of organic material into an environment where food is otherwise sparse and dispersed. The first changes appear quickly. Mobile scavengers gather, drawn by chemical traces that spread outward through the water. Fish and invertebrates move across the surface, removing soft tissue over the course of weeks to months, their activity methodical and continuous. The structure of the whale remains largely intact, yet it begins to shift, its outer layers thinning as the initial stage unfolds. As this phase concludes, a different community takes hold. Smaller organisms settle into the remaining tissues and exposed surfaces, breaking down what larger scavengers have left behind. Sediments around the carcass become enriched, supporting a growing assemblage of life that extends outward from the bones. The boundary of this influence is not sharply defined, but it can be traced through subtle changes in composition and activity. Within the skeleton itself, another process begins. Specialized organisms arrive that are adapted to access the nutrients locked within bone. Among them are worms that do not feed in the conventional sense, but instead extend root-like structures into the bone material, dissolving it gradually to extract the organic compounds within. These bone-eating worms, often delicate in appearance, form dense clusters along the surfaces, their presence marking a deeper stage in the transformation. Over time, the carcass becomes less recognizable as a single organism and more like a framework supporting a succession of communities. Each stage follows the one before, not as a replacement, but as a continuation, with overlapping processes that unfold at different rates. The timeline extends over years, sometimes decades, depending on conditions and the size of the original body. Throughout this period, the site functions as a localized center of activity within an otherwise quiet region. The influence of a whale fall extends beyond immediate consumption. It introduces nutrients into surrounding sediments, alters chemical balances, and provides a temporary structure that shapes how organisms interact in that space. Species that might not otherwise encounter one another are brought into proximity, their interactions forming patterns that persist until the resources are gradually exhausted. As the final stages approach, the remaining bones lose their structural integrity. What once held together as a recognizable form begins to fragment, its material dispersed into the surrounding environment. The communities that depended on it diminish, their numbers declining as the source that sustained them fades. The seafloor returns to a quieter state, though traces of the event remain embedded in the sediments. Such occurrences are rare when considered across the scale of the ocean, yet each one introduces a distinct period of change, shaping its surroundings in ways that linger long after the visible structure has disappeared. The process unfolds without interruption, guided by the steady work of organisms adapted to use what arrives from above. In these moments, a single descent becomes the foundation for a sequence that extends far beyond its origin, connecting distant regions through the gradual movement of matter and energy. Far from any shoreline, the seafloor begins to rise again, not gently, but in long, continuous elevations that stretch across entire ocean basins. These formations do not break the surface, yet they shape the structure of the planet in ways that remain largely unseen. Beneath kilometers of water, mountains extend upward, some reaching heights greater than Everest when measured from their base. The mid-ocean ridges form the longest mountain system on Earth, a connected chain that winds through the oceans for tens of thousands of kilometers. Along these ridges, tectonic plates move apart, allowing molten material from below to rise and solidify, creating new crust. This process unfolds slowly, measured in centimeters each year, yet over time it builds expansive structures that define the contours of the deep ocean floor. The ridges are not uniform. They are broken by valleys, intersected by faults, and shaped by the continuous movement of the crust beneath them. In some regions, the slopes are gradual, forming broad elevations. In others, steep walls descend into narrow rifts where the seafloor opens into deeper channels. These variations create a landscape that is complex and uneven, with features that mirror the diversity found on land, though formed under entirely different conditions. Rising from this terrain are seamounts, isolated peaks that stand apart from the larger ridge system. Some are remnants of volcanic activity, built over time as magma reached the seafloor and cooled into solid rock. Others are shaped by different geological processes, their origins traced through patterns in the surrounding crust. Many of these structures remain uncharted, their exact dimensions and locations still being mapped as exploration continues. As currents move through the ocean, they encounter these underwater mountains and are forced to adjust their paths. Water flowing across a seamount can be deflected upward, creating localized upwellings that bring nutrients from deeper regions toward higher layers. This movement influences the distribution of life, concentrating organisms in areas where conditions become more favorable. Around these elevations, the water can slow, swirl, or change direction, forming patterns that persist over time. The isolation of individual seamounts creates environments that are distinct from their surroundings. Species that inhabit one peak may remain separated from those on another, even when the distance between them is not large. Over time, this separation can lead to the development of unique forms of life, adapted to the specific conditions of their location. Differences in current flow, nutrient availability, and terrain contribute to this variation, shaping communities that reflect the character of each structure. Despite their scale, many of these underwater mountains have yet to be fully explored. Advances in mapping technology have revealed their presence, but detailed observation remains limited. Large areas of the ocean floor are still represented by incomplete data, with features inferred rather than directly observed. Each new survey adds detail, refining the understanding of a landscape that continues to emerge gradually. The presence of these hidden mountains alters more than the physical structure of the seafloor. They influence how water moves, how nutrients are distributed, and how ecosystems develop in their vicinity. Their effects extend beyond their immediate boundaries, shaping patterns that can be traced across wider regions. Beneath the surface, these elevations rise in silence, forming a network of structures that define the deep ocean's terrain, existing beyond view, yet integral to the planet's underlying form. Beyond the rising ridges and isolated peaks, the seafloor settles into an expanse so wide and level that it becomes difficult to perceive as terrain at all. The slopes ease, the variations diminish, and the landscape stretches outward in every direction with a quiet uniformity. These regions are known as abyssal plains, and they occupy more than half of the planet's surface, extending across the deep ocean in uninterrupted distances that surpass any environment on land. At first glance, they appear empty, a broad surface of fine sediment lying undisturbed. Yet this stillness is not the result of inactivity, but of processes that unfold at a scale far removed from immediate observation. Particles drift downward from higher layers, settling slowly through the water column before coming to rest on the seafloor. This material, composed of organic fragments, mineral dust, and microscopic remains, accumulates over time, forming a soft layer that blankets the underlying crust. The rate of this accumulation is remarkably slow. In some areas, only a few millimeters of sediment may be deposited over the course of 1,000 years. Each layer carries with it traces of the conditions that existed when it formed, preserving a record that extends far into the past. Variations in composition reflect changes in climate, ocean circulation, and biological activity, creating a timeline embedded within the seafloor itself. Life persists here, though it moves at a pace that mirrors the environment. Organisms adapted to these plains often grow slowly, reproduce infrequently, and rely on limited resources that arrive from distant regions. Many are small, their presence revealed only through careful observation, while others move across the sediment in measured patterns, leaving subtle traces that fade over time. The interactions between species are shaped by scarcity, each organism existing within narrow margins that define its survival. Exploration of these regions has been limited by their vastness and depth. While certain areas have been surveyed in detail, large portions remain mapped only in broad outlines, their finer features unresolved. Instruments descending to the seafloor capture brief moments, offering snapshots rather than continuous observation. The scale of the plains makes comprehensive study difficult, requiring time and resources that extend beyond what has yet been achieved. Despite this, each expedition contributes to a growing understanding of how these environments function. Samples retrieved from the sediment reveal layers that can be analyzed for chemical and biological content, providing insights into processes that operate over long timescales. These records allow researchers to reconstruct aspects of Earth's history, tracing shifts in temperature, productivity, and atmospheric composition through the materials preserved below. The apparent uniformity of the abyssal plains conceals subtle variations. Differences in sediment thickness, underlying geology, and current flow create distinctions that influence how life is distributed. In some areas, slight elevations or depressions alter the movement of water, concentrating material in ways that shape local conditions. These variations are often small in scale, yet they contribute to the overall complexity of the landscape. Across this immense expanse, the seafloor remains largely unchanged from moment to moment, its processes unfolding with a steadiness that resists rapid alteration. The plains extend beneath the ocean as a continuous presence, recording the passage of time in layers that accumulate almost imperceptibly, forming a landscape defined not by motion, but by persistence. In certain layers of the ocean, the presence of oxygen diminishes to levels so low that only a narrow range of organisms can persist. These regions do not form at the deepest points, nor do they occupy the surface. They exist in between, suspended within the water column, as zones where the balance between supply and consumption has shifted over time, creating an environment that restricts most forms of life. These areas are known as oxygen minimum zones. They develop where circulation is limited and biological activity consumes available oxygen faster than it can be replenished. Organic material drifting downward is broken down by microbes, a process that steadily reduces oxygen concentration. Without sufficient mixing from surrounding waters, this depletion continues until the environment reaches a state where only specially adapted organisms can endure. The boundaries of these zones are not sharply defined. Instead, oxygen levels decline gradually, forming layers that transition from more hospitable conditions to those that approach near absence. Within these gradients, life adjusts in response to subtle differences. Some species remain at the edges, moving carefully along the margins where oxygen is still present in small amounts, while others occupy the central regions, relying on metabolic processes that allow them to function under reduced conditions. As global temperatures shift, the structure of the ocean changes in ways that influence these zones. Warmer surface waters tend to mix less effectively with deeper layers, limiting the downward transport of oxygen. At the same time, metabolic rates can increase, leading to greater consumption of the oxygen that is already present. Together, these factors contribute to an expansion of oxygen minimum zones in certain regions, altering their depth and extent. This expansion affects how organisms move through the ocean. Species that rely on higher oxygen concentrations may be forced to adjust their vertical ranges, remaining within narrower bands where conditions remain suitable. Predators and prey that once occupied overlapping regions can become separated, changing patterns of interaction that have persisted over long periods. Some organisms adapt by modifying their physiology, while others shift their distribution, following the boundaries of oxygen availability as they change. The presence of these zones also influences chemical processes within the ocean. In low oxygen conditions, different pathways of nutrient cycling become more prominent, altering the balance of compounds such as nitrogen. These changes can extend beyond the immediate region, affecting productivity and ecosystem structure in surrounding waters. The effects are gradual, unfolding over time as the zones expand or contract in response to broader environmental shifts. Despite increasing attention, much about these regions remains uncertain. Measurements of oxygen levels are improving, yet the full extent of variability across different ocean basins is still being mapped. Long-term trends are emerging, but the pace and scale of change depend on multiple interacting factors that are not yet fully resolved. Observations continue to accumulate, each one adding detail to a system that is both dynamic and complex. Within these layers, the ocean reveals another form of limitation, one defined not by absence of light or extremes of pressure, but by the gradual fading of a fundamental resource. Life persists here in adjusted forms, shaped by constraints that narrow the possibilities of survival, yet do not eliminate them entirely. Some creatures of the deep do not become smaller in response to scarcity, but instead grow larger, their forms expanding beyond what is typical for their relatives in shallower waters. This pattern appears across different groups, emerging gradually rather than suddenly, until familiar shapes take on proportions that seem out of place when compared to their surface counterparts. Among the most recognizable examples are giant isopods, distant relatives of small crustaceans that inhabit coastal environments. In the deep ocean, these organisms can reach lengths of more than half a meter, their segmented bodies enclosed within armored plates that curve smoothly around them. Their movements are deliberate, their pace unhurried, reflecting an environment where energy is conserved and activity unfolds without urgency. The enlargement of these organisms has been observed in multiple species, suggesting that it is not the result of a single isolated factor. Instead, it appears to arise from a combination of conditions that characterize deeper regions of the ocean. Temperature plays a role, as colder environments tend to slow metabolic processes, allowing organisms to grow over longer periods without the same constraints found in warmer waters. This extended growth can lead to larger body sizes as development continues gradually across time. Pressure also contributes, though its influence is more complex. High pressure affects how biological structures are maintained, favoring forms that can distribute force evenly and avoid points of weakness. In some cases, larger body sizes may provide a more stable framework under these conditions, reducing the relative stress experienced by individual tissues. This relationship between size and structural integrity is subtle, shaped by interactions at both cellular and organismal levels. The availability of food introduces another dimension. In environments where resources are limited and arrive unpredictably, larger organisms may have an advantage in storing energy. A greater body mass allows for longer intervals between feeding events, supporting survival in conditions where nourishment is not consistently available. This capacity for storage aligns with the slow pace of life in these regions, where opportunities must be used efficiently. At the same time, alternative explanations continue to be considered. Some propose that reduced predation pressure in deeper waters allows organisms to grow larger without the same risks encountered elsewhere. Others suggest that oxygen levels, though lower than at the surface, may still support increased body size under certain conditions, particularly when metabolic rates are adjusted accordingly. These perspectives do not exclude one another, and the pattern of gigantism likely reflects an interplay of multiple factors rather than a single cause. The phenomenon extends beyond isopods, appearing in other groups such as certain amphipods and squids, each exhibiting its own variation on increased size. These occurrences are not uniform, and many species remain small despite sharing similar environments. This variation underscores the complexity of the processes involved, indicating that local conditions and evolutionary histories shape how gigantism emerges in different contexts. Observations of these organisms often occur during brief encounters, as exploration equipment passes through their habitat. The limited duration of these observations makes it challenging to determine how individuals grow, how long they live, and how their size influences their role within the ecosystem. Each recorded instance adds to a developing picture, one that continues to evolve as more data becomes available. Within the deep ocean, size does not follow a single predictable pattern. Instead, it reflects a balance of influences that shift gradually across environments, producing forms that expand beyond expectation while remaining shaped by the quiet constraints of their surroundings. Along the contours of the seafloor, movement takes on a form that resembles flow across land, though it remains hidden within the surrounding water. These currents do not spread evenly through the ocean. Instead, they gather, become denser, and begin to travel along the bottom, guided by the shape of the terrain beneath them. In certain regions, they follow defined paths, tracing routes that extend across great distances with a steadiness that recalls the quiet persistence of rivers. This movement arises from differences in density, created by variations in temperature and salinity. Colder, saltier water becomes heavier than the surrounding ocean, allowing it to sink and settle near the seafloor. Once there, it does not remain still. It begins to move laterally, influenced by gravity and the subtle gradients that exist across the ocean floor. Valleys, slopes, and channels guide its direction, shaping the current into streams that maintain their structure over long distances. As these currents travel, they carry with them material gathered from the regions where they formed. Nutrients, fine sediments, and dissolved compounds are transported along their path, linking distant parts of the ocean in a continuous exchange. What begins in one location may influence conditions far away as the current delivers its contents into new environments. This movement contributes to the distribution of resources, supporting ecosystems that depend on the arrival of material from elsewhere. The speed of these flows is often slow when measured directly, yet their persistence allows them to shape the seafloor over time. Sediments carried within the current can settle in certain areas, building layers that reflect the direction and strength of the flow. In other places, the current may erode the surface, removing fine particles and exposing underlying structures. These interactions create patterns that record the presence of movement, even when the flow itself is not directly observed. The structure of these underwater rivers is influenced by the surrounding environment. Changes in the seafloor can alter their course, diverting them into new channels or dispersing them into broader regions. Variations in temperature and salinity at their source can modify their density, affecting how they interact with other currents. These factors combine to produce a system that is both dynamic and difficult to predict in detail. Measuring these currents presents significant challenges. Their depth places them beyond the reach of many observation methods, and their slow movement requires long periods of monitoring to capture meaningful patterns. Instruments must remain in place for extended durations, recording subtle changes that reveal how the flow evolves over time. Even with these efforts, much of the system remains inferred rather than directly observed, pieced together from fragments of data collected across different regions. The presence of these flows contributes to a broader circulation within the ocean, connecting surface processes with the deep environment. They form part of a network that redistributes heat, nutrients, and chemical compounds, maintaining a balance that extends across vast distances. Their influence is not always visible, yet it is embedded in the structure of the seafloor and the composition of the water that surrounds it. Beneath the surface, these currents continue their steady movement, following paths shaped by the contours of the earth, carrying with them the quiet exchange of material that links one part of the ocean to another. There are formations on the seafloor that resemble stone ruins, rising in irregular clusters that seem too intricate to be purely geological. Their surfaces appear rigid, layered, and enduring, yet they are not carved from rock. They are built slowly and continuously by organisms whose structures are composed of glass. These are reefs formed by glass sponges, organisms that construct their bodies from silica, the same material found in sand and quartz. Within their tissues, silica is arranged into delicate frameworks, creating skeletons that are both strong and finely detailed. These structures interlock over time, forming larger networks that extend outward and upward, shaping the surrounding environment in subtle but lasting ways. For many years, formations like these were believed to belong only to the distant past. Fossil records showed that similar reefs had existed millions of years ago during periods when ocean conditions were different from those of today. It was assumed that such structures had disappeared, unable to persist in modern seas. This assumption remained in place until living reefs were identified again, not as remnants, but as active systems continuing to grow. Their rediscovery revealed that the conditions required for their formation had not entirely vanished. In certain regions, where temperature, depth, and water chemistry align, glass sponges continue to build these structures much as they once did. The process is gradual, unfolding over centuries as individual organisms contribute to a shared framework. Each sponge filters water, extracting microscopic particles, and in doing so supports both its own growth and the stability of the reef around it. The skeletons they produce are composed of silica fibers, arranged in patterns that provide both strength and flexibility. These fibers can fuse together, creating a rigid network that persists even after the organism itself has ceased to live. Over time, new sponges settle upon the existing framework, extending it further and reinforcing its structure. The reef becomes a layered construction, with older sections forming a foundation for continued growth. Some of these reefs have developed over thousands of years, their structures reflecting long periods of accumulation. The passage of time is recorded in their form, each layer representing a stage in their expansion. Unlike faster-growing systems, these reefs change slowly, their development measured in increments that are small but persistent. The presence of these formations influences the surrounding environment. Their complex shapes create spaces where other organisms can settle, providing shelter and surfaces for attachment. Water moving through the reef is filtered repeatedly, altering the composition of the local environment in ways that extend beyond the structure itself. The reef becomes a point of interaction where biological and physical processes converge. Despite their durability, these structures are vulnerable to disturbance. Their slow growth means that any damage is not easily repaired, and sections that are broken may take centuries to recover. The recognition of their existence has brought attention to their fragility, as well as to the limited understanding of how widespread they may be. Much about these reefs remains only partially known. Their full distribution, the range of species they support, and the exact conditions that allow them to persist are still being studied. Each observation adds detail, revealing a system that continues quietly, largely out of view. In these formations, material that begins as dissolved particles in seawater becomes part of something enduring, shaped into structures that persist across generations, holding within them the slow passage of time. At certain moments, the seafloor does not remain fixed. Layers that have settled over thousands of years can lose their balance and begin to move, not in small shifts, but in vast, coordinated collapses that travel across entire slopes. These events unfold beneath the ocean, hidden from direct view, yet they reshape the landscape in ways that exceed the scale of most processes on land. Sediment accumulates gradually along continental margins, forming thick deposits that rest upon inclined surfaces. Over time, these layers build up, their weight increasing, their internal structure shaped by the slow addition of particles and the pressure of what lies above. The stability of these deposits depends on a balance between gravity and the forces that hold the sediment together. When that balance is disrupted, movement can begin. Triggers for such collapses vary. A shift in tectonic activity can introduce vibrations that weaken the cohesion of the sediment. Changes in pressure caused by variations in water level or gas release within the layers can alter how the material behaves. Even the gradual accumulation of additional sediment can reach a point where the slope can no longer support its own weight. When failure occurs, it often begins in one location and then propagates outward, drawing larger sections into motion. As the sediment starts to move, it can accelerate, flowing downslope as a dense current that carries vast amounts of material. These underwater landslides can extend for hundreds of kilometers, displacing layers that have formed over immense spans of time. The movement is not always smooth. It can involve sudden shifts, fragmentation, and the creation of new contours along the seafloor as the material settles into different configurations. The impact of these events is not confined to the seafloor itself. When large volumes of sediment shift rapidly, they can displace the water above, generating waves that travel outward across the ocean. These waves, when they reach shallower regions, can become tsunamis, carrying energy from a disturbance that began far below. In some cases, evidence of past landslides has been linked to wave patterns preserved in coastal records, indicating that these hidden events can have far-reaching effects. Despite their significance, monitoring of underwater landslides remains limited. The depth at which they occur, combined with the vast areas involved, makes continuous observation difficult. Instruments placed on the seafloor can record changes locally, but capturing the full extent of an event requires coordination across wide regions, something that is still developing. Much of what is known comes from indirect evidence, such as the patterns left behind in sediment layers and the shapes of the seafloor revealed through mapping. These patterns show that such events are not rare over geological time. The seafloor bears the marks of repeated collapses, each one contributing to the ongoing reshaping of the landscape. Channels carved by past movements, deposits spread across lower regions, and abrupt changes in slope all point to a history of motion that continues quietly beneath the surface. The processes involved unfold at scales that are difficult to observe directly, yet they remain part of the ocean's broader system. Sediment that settles slowly over centuries can be redistributed in a matter of hours, altering the structure of the seafloor and influencing the conditions that follow. Within these hidden movements, the ocean reveals another way in which its surface stability is only an appearance, while below, the landscape continues to shift in ways that remain largely unseen. In the most remote depressions of the ocean, where the seafloor folds into its deepest forms, materials that began far above continue their descent, carried slowly through the water column until they settle in places few currents disturb. Among these materials are fragments that did not originate from natural processes, pieces shaped elsewhere and introduced into the ocean through pathways that extend across the surface world. These fragments are microplastics, particles reduced over time from larger objects into forms small enough to drift with ease. They enter the ocean through rivers, coastal runoff, and direct disposal, dispersing outward and downward as they break apart. Their journey does not end near the surface. Gradually, they sink, sometimes attached to organic matter, sometimes settling on their own, moving through layers until they reach the seafloor. Even in the deepest trenches, these particles have been found embedded within the sediment. Their presence in such locations reflects the reach of processes that connect distant environments. What begins in one region can travel across oceans, guided by currents and gravity, until it arrives in areas that remain otherwise isolated. The descent is slow but persistent, and over time it leads to accumulation in places that were once thought to be beyond such influence. Within the sediment, microplastics mix with natural particles, becoming part of the layered record that continues to form. Their composition differs from the surrounding material, yet they do not remain separate. They settle into the same spaces, influenced by the same processes that shape the seafloor. As layers build, these fragments become incorporated into a system that changes gradually, preserving their presence within its structure. The interaction between these particles and deep ocean life is not yet fully understood. Some organisms encounter them as they move through the sediment or filter material from the water. Ingested particles may pass through without immediate effect, or they may interact with biological systems in ways that are still being studied. The scale of these interactions remains difficult to measure, as observations are limited and conditions vary across different regions. The persistence of plastic contributes to this uncertainty. Unlike many natural materials, it does not break down quickly. Its structure allows it to remain intact over long periods, altering slowly through processes that occur at rates difficult to observe directly. As a result, once it reaches the deep ocean, it is likely to remain there, accumulating alongside the natural components of the seafloor. The pathways that lead to this distribution are complex, shaped by surface activity, ocean circulation, and the gradual movement of particles through the water column. Each stage of this journey influences where and how these fragments settle. Variations in density, size, and attachment to other materials determine whether they remain suspended for longer periods or descend more quickly to the bottom. Research into this presence continues to expand, with new sampling efforts revealing additional locations where microplastics have accumulated. These findings contribute to a growing understanding of how materials introduced at the surface can extend their influence across the entire ocean. The full implications of this distribution, particularly in the deepest regions, are still being examined. Within the sediments of the deepest trenches, these fragments remain as part of a broader system, their presence reflecting a connection between distant environments that unfolds quietly over time. From samples that appear almost empty at first glance, entire communities begin to emerge once they are examined at a finer scale. A small volume of water, a thin layer of sediment, even the surface of a single organism can contain traces of life that do not reveal themselves through direct observation. Instead, they appear through fragments of genetic material, sequences that indicate presence without requiring the organism to be seen. Advances in genetic sampling have made it possible to detect these traces with increasing precision. By collecting environmental DNA, researchers can identify organisms based on the genetic signatures they leave behind, whether through cells, waste, or microscopic fragments drifting in the water. This approach does not rely on capturing or observing the organism itself. It reveals existence through patterns embedded in the material that surrounds it. The results have expanded the known diversity of the ocean far beyond earlier expectations. Sequences appear that do not match any recorded species, suggesting the presence of forms that have not yet been described or classified. In many samples, these unknown sequences outnumber those that correspond to known organisms, indicating that the majority of life in these environments remains unnamed. This pattern is not limited to a specific region. It appears across different depths, from midwater layers to the deepest sediments, reflecting a widespread gap between what is present and what has been formally documented. Each new data set adds to a growing collection of genetic information, yet much of it cannot be assigned to a known organism. The reference libraries used for comparison continue to expand, but they remain incomplete. The process of identifying and describing species is inherently slow. It requires more than detecting genetic material. Physical specimens must be collected, examined, and compared with existing records. Characteristics must be documented, relationships established, and distinctions clarified. In the deep ocean, where access is limited and observation is brief. Obtaining the necessary material for this process can take significant time and effort. Even when specimens are collected, the work of classification extends further. Many organisms exhibit subtle differences that are not immediately apparent, requiring detailed analysis to determine whether they represent new species or variations of known ones. Genetic data can suggest distinctions, but it must be integrated with physical and ecological information to form a complete understanding. The scale of the task becomes clear when considering the extent of the ocean and the variety of environments it contains. Each region supports its own assemblage of life, shaped by local conditions that influence how species develop and interact. As exploration continues, new areas are sampled, each one contributing additional sequences that expand the range of what is known, while also increasing the number of unknowns. The gap between discovery and description reflects both the richness of these environments and the limits of current methods. Technology allows detection to proceed rapidly, revealing patterns that extend beyond direct observation. Yet, the process of translating those patterns into formal knowledge moves at a different pace. The result is a growing awareness of how much remains to be understood. Within this expanding field of data, the ocean reveals a complexity that cannot be fully captured in a single moment. The presence of unknown species is not an anomaly, but a consistent feature emerging from each sample as part of a broader system that continues to unfold gradually, shaped by processes that extend beyond immediate perception. The outlines we have of the seafloor often appear complete when viewed from a distance, smooth gradients and continuous shapes that suggest a finished map. Yet these representations are built from signals that lose detail as they travel, translating vast spaces into simplified forms. Beneath this surface of apparent clarity, much of the ocean floor remains only loosely defined, its finer structures still unresolved. Mapping the deep ocean relies primarily on sound. Pulses are sent downward, and the echoes that return are used to estimate distance and shape. Over large areas, this method provides broad coverage, allowing researchers to trace the contours of ridges, plains, and trenches. However, the resolution of these maps depends on how closely the measurements are spaced. When data points are far apart, smaller features blend into the background, their presence smoothed into the surrounding terrain. Higher resolution mapping requires more detailed surveys, with instruments moving closer to the seafloor and collecting data at finer intervals. Autonomous and remotely operated vehicles can achieve this level of detail, revealing structures that remain invisible in broader scans. Yet, the area they can cover is limited, and each mission requires careful planning, time, and resources. As a result, only selected regions have been mapped with this degree of precision. The scale of the ocean presents a significant challenge. Covering more than half the planet, the deep sea floor extends across distances that would take decades to survey, even with sustained effort. Each section must be approached methodically, with equipment that can operate reliably under conditions that restrict access and communication. The process cannot be rushed, as accuracy depends on repeated passes and careful calibration. Cost adds another layer of limitation. Deploying research vessels, maintaining specialized equipment, and supporting the teams required for these missions involves substantial investment. Funding must be balanced across multiple priorities, and mapping efforts compete with other areas of study. This influences how often surveys can be conducted and which regions are selected for detailed exploration. Even with advances in technology, the process remains gradual. Improvements in sonar systems, data processing, and autonomous navigation have increased efficiency, allowing more area to be covered in less time. Satellite measurements provide additional information by detecting variations in the ocean surface that reflect underlying structures. However, these methods offer indirect insights, requiring further verification through direct observation. The result is a layered understanding of the seafloor. Broad maps outline the general form, while detailed surveys fill in specific areas with greater clarity. Between these levels lies a gap where features exist but have not yet been resolved. This gap represents not an absence of knowledge, but an ongoing process of refinement, where each new dataset adds detail to what was previously inferred. As mapping continues, previously unrecognized structures come into view. Small elevations, subtle depressions, and complex formations emerge from the data, altering the perception of regions that once appeared uniform. These discoveries reshape the understanding of how the seafloor is organized, revealing patterns that extend beyond initial expectations. The completion of a fully detailed map remains a long-term objective. The pace at which it can be achieved is shaped by the interplay of technology, resources, and the vastness of the environment itself. Each survey contributes a portion of the whole, building a representation that becomes clearer over time, yet still incomplete in its finer details. Within this process, the ocean floor remains partially hidden, its full structure unfolding gradually as mapping progresses. Reaching the deepest parts of the ocean is not simply a matter of distance, but of enduring conditions that steadily resist intrusion. Every meter of descent increases the demands placed on any structure that attempts to travel downward, compressing surfaces, testing seals, and narrowing the margin between stability and failure. The journey becomes less about movement and more about maintaining integrity within an environment that applies force without interruption. Pressure defines this challenge. As depth increases, the weight of the water above accumulates, pressing inward from every direction with uniform intensity. At the greatest depths, this force becomes immense, capable of deforming materials that perform reliably elsewhere. To withstand it, submersibles must be constructed from carefully selected materials, shaped into forms that distribute stress evenly. Spheres are often used for crew compartments, as their geometry reduces points of weakness, allowing the structure to hold against the surrounding force. The thickness of these structures reflects the conditions they must endure. Walls composed of specialized alloys or composite materials are designed to resist compression while maintaining a balance between strength and weight. Every opening, every joint, must be sealed with precision, as even minor imperfections can become critical under sustained pressure. The design process involves not only engineering calculations, but also repeated testing, ensuring that each component performs as expected before it is exposed to the depths. Descent itself is a controlled process. Submersibles adjust their buoyancy through ballast systems, allowing them to sink gradually. The rate of descent must be managed carefully, as rapid changes can introduce stress and reduce stability. As the vehicle moves downward, communication with the surface becomes more limited, relying on acoustic signals that travel slowly and carry only small amounts of information. The connection remains, but it becomes distant, reduced to brief exchanges that mark progress and confirm status. Time at depth is constrained. Dive windows are limited by both technical and environmental factors. Power reserves determine how long systems can operate, while the need to maintain safety margins restricts how close operations can approach their limits. Weather conditions at the surface influence when launches and recoveries can occur, as rough seas complicate the handling of equipment. Each mission must be planned within these boundaries, balancing the desire for observation with the requirement for a safe return. Only a small number of manned descents have reached the deepest regions. Each of these journeys represents a significant effort involving years of preparation and coordination. The rarity of these missions reflects the complexity of the undertaking as well as the resources required to support it. Most exploration now relies on remotely operated or autonomous systems which can reach similar depths without placing human occupants at risk. Even so, these systems face many of the same challenges, requiring careful design to function reliably under extreme conditions. At the seafloor, movement is slow and deliberate. Visibility is limited, and navigation depends on instruments that interpret the surroundings through sound and light emitted by the vehicle itself. Observations must be made within the constraints of available time, each moment contributing to a record that will be analyzed later, far from the depths where it was gathered. The effort to reach these regions reflects a balance between human curiosity and the physical realities of the environment. Progress continues through incremental improvements, each advancement extending the range of what can be achieved while maintaining the stability required to return. In regions where sunlight never arrives, life continues by drawing from sources that do not depend on the sky. Energy emerges instead from chemical differences, from reactions that occur where contrasting substances meet and exchange. In these environments, the absence of light does not halt biological activity. It redirects it, shaping systems that operate through pathways less familiar to those observed at the surface. Chemosynthesis forms the foundation of this process. Certain microorganisms use chemical reactions to convert inorganic compounds into energy, supporting their growth and reproduction. Substances such as hydrogen sulfide, methane, and other reduced chemicals provide the necessary input, allowing these organisms to build organic matter without relying on photosynthesis. This transformation occurs at a scale that is both microscopic and extensive, forming the base of ecosystems that extend outward from these reactions. The presence of such systems alters the understanding of where life can exist. Conditions once considered too isolated from traditional energy sources are now recognized as capable of supporting complex communities. Organisms that rely on chemosynthesis form relationships with others, creating networks of interaction that mirror, in structure if not in detail, those found in environments influenced by sunlight. These connections demonstrate that life can organize itself around different forms of energy, adapting its processes to the resources available. The implications of this realization extend beyond the ocean. Environments elsewhere, lacking direct access to sunlight, may still provide the conditions necessary for similar processes to occur. Subsurface oceans, icy layers, and chemically active regions could support life forms that rely on energy derived from internal planetary processes rather than external radiation. The study of chemosynthetic systems offers a framework for considering these possibilities, grounding them in observations made within Earth's own environments. This perspective has influenced how exploration is approached. When searching for life beyond Earth, attention is given not only to the presence of light, but to the availability of chemical gradients that can sustain metabolic activity. Instruments are designed to detect signs of such processes, focusing on indicators that reflect the presence of energy conversion in environments that do not resemble those at the surface of our own planet. Despite this broader view, the systems within the deep ocean remain subjects of ongoing study. The exact mechanisms by which different organisms utilize chemical energy continue to be examined, as do the relationships that form between species within these communities. Variations in chemical composition, temperature, and pressure influence how these systems develop, creating a diversity of forms that reflects the conditions in which they arise. The persistence of these ecosystems also raises questions about their origins. The early Earth may have supported similar processes before the widespread presence of oxygen and the development of photosynthesis. In this context, chemosynthesis provides a possible pathway for the initial establishment of life, offering a model that aligns with conditions believed to have existed in the planet's early history. Within these environments, energy flows in a manner that remains steady and self-contained, independent of cycles driven by sunlight. The systems that emerge from this flow continue to function as long as the chemical conditions that sustain them remain in place. The recognition of life without sunlight reshapes expectations, suggesting that biological processes can arise and persist under conditions that differ from those once assumed to be necessary. Far below the surface, carbon moves through the ocean in a cycle that unfolds without visibility, guided by processes that operate over long spans of time. This movement does not follow a single path. It disperses, settles, transforms, and circulates, connecting distant regions through exchanges that are rarely observed directly. Within the deep ocean, carbon becomes part of a system that holds it in place, while also allowing it to move slowly through layers of water and sediment. Material from above begins this process. Organic matter, formed in sunlit regions, drifts downward as particles that vary in size and composition. Some are consumed along the way, broken down by organisms that inhabit the water column. What remains continues its descent, eventually reaching depths where further decomposition slows. In these regions, carbon becomes incorporated into sediments or dissolved within the surrounding water, contributing to a reservoir that extends across vast areas. The deep ocean serves as one of the largest storage systems for carbon on the planet. Once carbon reaches these depths, it can remain there for extended periods, isolated from rapid exchange with the atmosphere. This separation is maintained by the structure of ocean circulation, which moves water through a series of pathways that operate at different speeds. Surface waters interact more readily with the air, exchanging gases and responding to changes in temperature and pressure. Deeper waters move more slowly, carrying their contents along routes that may take centuries to complete. This circulation connects regions that are far apart. Water formed in one area can travel across entire ocean basins before returning toward the surface. As it moves, it transports dissolved carbon along with it, redistributing material in a gradual, continuous flow. The pace of this movement shapes how carbon is stored and released, influencing the balance between what remains in the ocean and what returns to the atmosphere. The interaction between deep ocean storage and climate is subtle, yet significant. By holding large quantities of carbon below the surface, the ocean reduces the amount present in the atmosphere, contributing to a balance that affects global temperature. Changes in circulation patterns, temperature, or biological activity can alter this balance, modifying how carbon is partitioned between different parts of the system. Within sediments, carbon can remain preserved for even longer periods. Layers accumulate slowly, each one containing traces of past conditions. Over time, these layers form records that can be examined to understand how carbon has moved through the system across different eras. Variations in composition reflect shifts in productivity, circulation, and environmental factors, offering insight into processes that extend beyond immediate observation. The pathways that govern this cycle are not fixed. They respond to changes in the ocean's structure, influenced by factors such as temperature gradients and the formation of water masses at the surface. As these factors evolve, the routes and rates of carbon transport adjust accordingly, introducing variations that can have long-term effects. Despite advances in measurement, many aspects of this cycle remain only partially resolved. The deep ocean is vast, and direct observations are limited in both space and time. Models and indirect data provide an understanding of the general patterns, yet finer details continue to be refined as new information becomes available. Within this hidden system, carbon moves with a steadiness that reflects the scale of the ocean itself, circulating through depths where its presence shapes conditions in ways that are gradual, persistent, and closely linked to the broader dynamics of the planet. Across the vast middle depths of the ocean, there is a region that does not draw attention through visible structure, yet holds more life than any other on the planet. It stretches horizontally across entire basins and vertically through a range where sunlight no longer defines the environment, forming a continuous habitat that surrounds the globe in quiet persistence. This region, often called the Midnight Zone, contains a large portion of Earth's living biomass, not concentrated in dense clusters, but dispersed through open water. Organisms here exist in numbers that accumulate across immense space. Individually, many are small, delicate, and difficult to detect. Together, they form a living presence that extends far beyond what is immediately apparent. The distribution of life in this zone differs from that of environments shaped by visible structure. There are no fixed surfaces to gather around, no clear boundaries that define where one community ends and another begins. Instead, organisms are suspended within the water itself, moving slowly or drifting with currents that pass through without leaving permanent traces. Their presence is revealed not through direct observation alone, but through patterns that emerge when measurements are taken across large areas. Biomass here is unevenly distributed, influenced by factors that operate over wide scales. Nutrients arriving from above, carried downward through gradual processes, provide a foundation that supports life throughout this region. These inputs are not constant, and their variability shapes how organisms are spread across different depths. Some areas hold higher concentrations, while others remain sparse, creating a landscape defined by gradients rather than clear divisions. Movement plays a role in this distribution. Many organisms shift their position over time, adjusting their depth in response to changes in conditions. This motion contributes to the blending of communities, linking different layers in ways that are not immediately visible. The result is a system where boundaries are fluid, and the concept of a fixed location becomes less distinct. Despite its scale, much of this habitat remains only partially observed. Traditional methods of exploration, focused on surfaces and structures, capture only fragments of what exists here. Instruments passing through the water column record brief encounters, revealing isolated details without fully capturing the continuity of the environment. The vastness of the region means that even extensive surveys cover only a small portion of its total extent. Advances in technology have begun to expand what can be detected. Acoustic measurements, imaging systems, and sampling techniques provide new ways to observe organisms that were previously overlooked. These tools reveal patterns that suggest a level of complexity, extending beyond earlier expectations. Yet, they also highlight how much remains unmeasured. The perception of emptiness in this region arises from the difficulty of observing it directly. Without visible landmarks or concentrated activity, the water can appear uniform, its contents hidden within a medium that does not easily reveal detail. This impression shifts as more information is gathered, showing that the absence of visible structure does not correspond to an absence of life. Within this broad expanse, the ocean holds a form of abundance that is defined by scale rather than density, existing as a continuous presence that spans the planet, largely unseen yet integral to its living systems. For a long time, the ocean below a certain depth was imagined as a place where little happened. The absence of light suggested absence of activity, and early observations, limited by the tools available, seemed to support that idea. What could not be seen or easily reached was often interpreted as simple, a quiet extension of the surface world, stripped of complexity. This belief shaped the direction of exploration. Efforts focused on regions that were accessible, where direct observation could confirm expectations. The deeper layers remained largely unexamined, not because they were unimportant, but because they were assumed to hold less of interest. Instruments that descended into these depths returned with incomplete data, reinforcing the impression that there was little to find. The concept of emptiness was also influenced by the way the ocean was measured. Early sampling methods collected only small amounts of material, often missing organisms that were sparse or delicate. Nets passed through vast volumes of water without capturing the full range of life present. What was retrieved appeared limited, and this limitation was taken as evidence of the environment itself rather than a reflection of the methods used. As technology advanced, this perception began to shift. New instruments allowed for more precise observation, revealing patterns that had previously gone unnoticed. Cameras captured images of organisms moving through depths once considered barren. Acoustic measurements detected layers of activity where none had been expected. Each new observation added detail to a picture that was gradually becoming more complex. The realization that the ocean was not empty required a change in perspective. Instead of viewing the deep as a void, it became necessary to consider it as a system operating under different conditions. Life there did not follow the same patterns as in illuminated regions. It was distributed differently, often less concentrated, and adapted to constraints that shaped its presence in subtle ways. Historical assumptions had delayed this recognition. By framing the deep ocean as lacking in activity, early interpretations influenced the questions that were asked and the methods that were used. Exploration proceeded within those boundaries, reinforcing the initial belief. Only when those assumptions were set aside did the evidence begin to accumulate in a way that revealed the true extent of the environment. The shift in understanding was not immediate. It unfolded over time as observations from different regions and methods converged. Each piece of data contributed to a broader reassessment, showing that what had been overlooked was not absence, but a form of presence that required different approaches to detect. This pattern reflects a broader aspect of scientific inquiry. What is expected can shape what is observed, guiding attention towards certain possibilities while leaving others unexplored. When expectations change, the same environment can reveal new features, not because it has altered, but because it is being examined with a different perspective. The deep ocean, once thought to be empty, now appears as a space filled with activity that extends across scales, both large and small. Its complexity does not always present itself directly, but it becomes apparent through careful observation and the gradual accumulation of evidence. Within this shift, the ocean offers a reminder that absence of evidence is not evidence of absence, and that understanding often depends on the willingness to look beyond initial assumptions. Progress in understanding the deep ocean does not arrive in sudden shifts, but in small, carefully measured increments. Each new observation is placed alongside those that came before, forming a picture that expands gradually rather than all at once. The pace of this process reflects the conditions under which knowledge is gathered, shaped by constraints that extend far beyond the questions themselves. Time is one of the primary factors. Many processes in the deep ocean unfold over long periods, often beyond the duration of a single expedition. Changes in ecosystems, movement of water masses, and accumulation of material occur slowly, requiring repeated observations to identify patterns. A brief visit can reveal only a moment within a larger sequence, leaving the broader context to be assembled over years of study. The intervals between observations further extend this timeline. Expeditions to deep regions are not continuous. They are planned, scheduled, and carried out within limited windows, often separated by months or years. Data collected during one mission must be analyzed, compared, and integrated before the next opportunity arises. This cycle creates a rhythm where discovery is followed by interpretation, then by preparation for further exploration. Cost influences how frequently these missions can take place. Operating research vessels, deploying specialized equipment, and maintaining the infrastructure required for deep ocean work involve significant resources. Funding must support not only the expeditions themselves, but also the development and maintenance of the tools used to carry them out. These demands limit the number of projects that can proceed at any given time, shaping the pace at which new information is gathered. Access remains another defining constraint. The deep ocean is not easily reached, and each descent requires careful coordination. Equipment must function reliably under conditions that restrict movement and communication. Human presence at these depths is rare, and even remotely operated systems face limitations in range and endurance. As a result, many regions are visited only briefly, leaving large areas unobserved for extended periods. The data that emerges from these efforts often arrives in fragments: a sample from one location, a series of images from another, measurements taken along a specific path. Each piece contributes to understanding, yet none provides a complete view on its own. Researchers must combine these fragments, identifying connections and patterns that extend beyond individual observations. This synthesis takes time, requiring careful analysis and comparison across different data sets. Technological development introduces its own timeline. Improvements in sensors, vehicles, and analytical methods expand what can be observed, but these advancements occur gradually. New tools must be designed, tested, and refined before they can be applied widely. As capabilities increase, previously inaccessible aspects of the deep ocean become observable, adding new layers to the existing body of knowledge. The cumulative effect of these factors is a form of progress that is steady but deliberate. Each step builds upon the last, creating a foundation that supports further exploration. The process does not accelerate easily, as it depends on conditions that cannot be bypassed. Instead, it advances through persistence, with each contribution adding detail to a system that is revealed over time. Within this framework, the deep ocean shapes the way science develops, guiding it along a path where understanding emerges slowly, aligned with the pace of the environment itself. 50 years ago, the deep ocean was described with a confidence that now feels incomplete. It was understood as a region defined by absence, lacking the complexity and activity found closer to the surface. The tools available at the time offered only limited glimpses, and from those glimpses, a picture was assembled that seemed coherent, if simplified. Descriptions focused on uniformity. The seafloor was often portrayed as a broad, quiet expanse, with life present but sparse, adapted to conditions that restricted diversity and interaction. Energy was thought to arrive almost entirely from above, carried downward in diminishing amounts, shaping ecosystems that depended on what filtered through from the surface. The absence of light reinforced this view, suggesting a system that operated with limited inputs and correspondingly limited outcomes. As exploration expanded, this framework began to shift. New methods revealed environments that did not align with earlier expectations. Instead of uniformity, variation became apparent. Regions once assumed to be similar were found to differ in structure, chemistry, and biological composition. Each discovery added detail, challenging the idea that the deep ocean could be described through a single, consistent model. The recognition of alternative energy pathways marked a significant change. Systems driven by chemical processes demonstrated that life could organize itself independently of sunlight, introducing a form of productivity that had not been fully considered. This expanded the range of conditions under which ecosystems could exist, altering the understanding of how energy moves through the ocean. At the same time, observations of movement and distribution revealed patterns that extended across large scales. Organisms were found to migrate, to interact, and to form communities that were more dynamic than previously assumed. The perception of stillness gave way to an awareness of activity that was subtle yet continuous. Technological advancements played a central role in this transition. Improvements in imaging, sampling, and measurement allowed researchers to observe details that had once been beyond reach. Each new capability provided access to aspects of the environment that had been inferred rather than directly seen. As these observations accumulated, they reshaped the framework through which the deep ocean was understood. The rate of change in this understanding has been notable. Within a relatively short span of time, many of the assumptions that once defined the field have been revised. What was considered complete has been expanded, and what was thought to be simple has been revealed as complex. This progression reflects not only the accumulation of data, but also the willingness to reconsider earlier interpretations in light of new evidence. Despite this progress, the process remains ongoing. Each answer introduces additional questions, extending the boundaries of what is known. The deep ocean continues to present conditions that require careful study, and the pace of discovery remains aligned with the methods used to explore it. Looking back, the contrast between past and present understanding highlights how knowledge develops over time. Early descriptions provided a foundation, but they were shaped by the limits of observation. As those limits have shifted, so too has the picture that emerges. The deep ocean, once framed within narrow expectations, now appears as a system of considerable depth and variation, its full extent still unfolding as exploration continues. Even as the picture of the deep ocean has expanded, there remain areas where understanding pauses, not from lack of interest, but from the limits of what has been observed and measured. These gaps are not empty spaces waiting to be filled quickly. They are regions where complexity extends beyond current resolution, where patterns are visible but not yet fully interpreted. One of the most persistent uncertainties lies in the total diversity of life. Estimates of species numbers continue to shift as new methods reveal organisms that were previously undetected. Genetic data suggests a scale of biodiversity that exceeds earlier expectations, yet translating these signals into confirmed species remains an ongoing process. The boundaries between species, the relationships among them, and the full extent of their distribution are still being refined, leaving the total count as a moving target rather than a fixed number. In parallel, questions remain about the stability of methane stored beneath the seafloor. Deposits that appear stable under current conditions may respond to changes in temperature or pressure in ways that are not yet fully predictable. Observations indicate that some regions release methane gradually, while others retain it over long periods. The factors that determine this behavior involve interactions between geological structure, chemical composition, and environmental change, forming a system that is understood in parts but not as a complete whole. The ecosystems within the deepest trenches present another area of incomplete knowledge. While individual species have been observed and certain adaptations have been identified, the full structure of these communities remains only partially described. Interactions between organisms, the flow of energy through the system, and the ways in which these ecosystems respond to external influences are still being pieced together. Each descent provides new information, yet the continuity of these environments over time is difficult to capture. Long-term geological processes add further layers of complexity. The seafloor is shaped by forces that operate over timescales far beyond direct observation, including the movement of tectonic plates, the formation of new crust, and the gradual alteration of existing structures. These processes influence the distribution of habitats, the availability of chemical resources, and the overall configuration of the ocean floor. Understanding how these changes interact with biological systems requires integrating data from multiple fields, each with its own methods and timelines. The connections between these areas of uncertainty highlight the interconnected nature of the deep ocean. Biodiversity is influenced by geological conditions. Methane stability affects chemical environments, and ecosystem structure depends on both biological and physical factors. These relationships create a network of dependencies that complicates efforts to isolate individual variables. Advances in technology and methodology continue to reduce these uncertainties, yet each improvement also reveals additional layers of detail. As resolution increases, so does the recognition of variability, showing that processes once thought to be uniform can differ across regions and over time. This expanding detail requires careful interpretation, ensuring that new information is integrated without oversimplifying the systems it describes. Within these unresolved areas, the deep ocean maintains a degree of complexity that resists quick explanation. Observations accumulate, patterns emerge, and models are refined, but the full picture remains incomplete. The process of understanding continues, shaped by the gradual addition of knowledge and the recognition of how much remains to be explored. There is a quiet shift that happens as knowledge deepens, not a movement toward certainty, but toward a clearer sense of how much remains unresolved. In the study of the deep ocean, each discovery does not close a chapter so much as adjust its direction, refining what was once assumed and placing it within a broader, more intricate context. Early interpretations often carry a sense of completion, shaped by the limits of available evidence. With time, those interpretations are revisited, not discarded entirely, but revised. Details are added, relationships are reconsidered, and patterns that once seemed stable reveal layers of variation. This process does not diminish what came before. It places it within a continuum, where understanding evolves through careful correction rather than abrupt replacement. In this way, science moves as a sequence of refinements. Observations lead to models, models guide further observation, and the results return to reshape the original framework. Each step depends on the ones that preceded it, forming a progression that is both cumulative and adaptive. The deep ocean, with its scale and inaccessibility, makes this process especially visible, as each new piece of information carries weight against a background of limited data. Correction becomes a central feature of discovery. When new evidence emerges, it often reveals that earlier explanations were incomplete, shaped by perspective and constraint. Adjusting those explanations requires a willingness to reconsider assumptions, to accept that clarity can change as new information becomes available. This openness is not a weakness. It is a condition that allows understanding to expand. The environment itself reinforces this approach. Conditions vary across depth, location, and time, creating a system where uniform explanations rarely hold. Patterns observed in one region may differ in another, requiring interpretations that can accommodate variability. This complexity encourages a form of thinking that remains flexible, attentive to nuance, and aware of the limits of generalization. As knowledge accumulates, the sense of certainty becomes more measured, not because less is known, but because the context of that knowledge becomes wider. Each answer is accompanied by new considerations, extending the range of what must be understood. This expansion does not lead to confusion, but to a more grounded awareness of how systems operate across different scales. The role of technology, data, and analysis supports this progression, yet it does not eliminate uncertainty. Instruments provide clearer views, measurements become more precise, and models grow more detailed, but each improvement also reveals additional layers. The process remains open, guided by evidence that continues to develop over time. Within this ongoing effort, the act of exploration takes on a particular character. It is not driven by the expectation of final answers, but by the recognition that understanding is built gradually. Each observation contributes to a larger picture that is never fully complete, yet increasingly coherent. The deep ocean, in its scale and subtlety, reflects this dynamic. It offers information that reshapes perspective, inviting adjustments that bring knowledge closer to the systems it seeks to describe. In doing so, it highlights a principle that extends beyond any single field, that discovery is not a destination, but a continuous process of refinement, guided by attention, patience, and the steady integration of what is newly seen. There is a boundary beneath the surface that is not marked by a line, but by a gradual fading of what is familiar, where light gives way to depth and certainty softens into possibility. Beyond that boundary lies a world that has been present for as long as the planet itself, unfolding quietly, largely untouched by direct observation, holding its details with a kind of steady patience. Across this immense expanse, the deep ocean extends as the largest continuous environment on Earth, yet much of it remains only lightly traced. What has been seen forms a collection of glimpses, each one precise, each one valuable, but together still incomplete. Between those glimpses are distances that have not yet been crossed, spaces where processes continue without interruption, shaping conditions that are only partially understood. The scale of this frontier does not announce itself through noise or sudden change. It reveals itself slowly, through the accumulation of small observations that begin to suggest something larger. A pattern detected here, a structure identified there, each contributing to a sense that what lies beneath is not a single mystery, but many, layered and interconnected. What has emerged so far does not point toward something chaotic or unknowable, but toward a system that is intricate and consistent, governed by principles that are gradually becoming clearer. The unfamiliarity comes not from disorder, but from distance, from the simple fact that these environments have existed beyond regular human reach for most of history. In this way, the deep ocean does not present itself as something to be feared, but as something to be approached with care and attention. Its vastness places individual discoveries within a broader context, where each finding becomes part of a larger effort to understand how the planet functions as a whole. The sense of scale encourages a perspective that is measured, recognizing both what has been learned and what remains open. There is a quiet humility in this process. The more that is observed, the more apparent it becomes that current knowledge represents an early stage in a much longer exploration. Techniques will improve, coverage will expand, and patterns that are now only hinted at will come into clearer focus. Yet even as this happens, the horizon of understanding will continue to extend outward, maintaining a balance between discovery and uncertainty. The deep ocean, in this sense, serves as a reminder of how exploration unfolds. It is not a movement toward a final conclusion, but an ongoing engagement with a system that reveals itself gradually. Each descent, each measurement, each moment of observation adds to a narrative that is still being written, one that reflects both the persistence of inquiry and the scale of what is being explored. As this quiet frontier continues to open, it offers an invitation that does not demand urgency. It simply remains present, waiting to be observed more closely, understood more deeply, approached with the same steady curiosity that has carried exploration this far. If following these slow passages into the unknown is something you find yourself returning to, a simple gesture of support helps sustain the journey, allowing these explorations to continue, one careful step at a time.